All right, this is Algebra 2, Chapter 11, Section 1. It's Permutations and Combinations. And our learning objective is to count permutations and to count combinations. One item that we're going to use, and anytime the word fundamental is in the definition or in the title, know that it's highly important. So make sure you guys have written down 11-1, permutations, combinations. If you want to be even more superstar stud, you can write the word notes, so that when I grade it, it says the word notes on it, and I know it's your notes. Because sometimes I can't tell. Make sure you have your learning objective written down as well, because it's kind of important to know what you're learning. Alright, so we're going to talk about the fundamental counting principle. If an event M can occur in M ways and is followed by event capital N that can occur in N ways, then event M followed by event N can occur in the product of M times N ways. And I know that's a really hard way of saying it, which is why they put the example down. So 3 pants and 2 shirts give you 3 times 2 equals 6 possible outfits. So you just multiply the items together to give you the total amount of possibilities. The license plate problem is a classic when looking at this fundamental counting principle. So the photos show Maryland license plates in 2004 and in 1912. How many more 2004 style license plates were possible than the 1912 style plates? So you want to look at it, and I do this by, I make a little line to represent each item that I'm looking for. So in this case I have 3 letters, 1, 2, 3, and 3 numbers, 3 digits, 2, 3. So I have 6 altogether. So how many possibilities are there for this first letter? You look, and there are 26 letters in the alphabet, so there are 26 possibilities for that first slot. And then for the second slot, also 26. The third slot, also 26. Now, the second 3 items, if you try to, some people will go, oh, there's only 9 numbers between 1 and 9. But we can use 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So including 0, there are 10. And all you're going to do is multiply all these guys together to get 17,576,000. All right, so let's go back into the olden days, and we're going to use 4 digits. So you make 4 slots for each item and put the possibilities in each slot. So these digits are 0 through 9, which is 10. That's 10 times 10 times 10 times 10, or 10,000. And then because the problem asks for how many more, we subtract the 2, and there are only 17,566,000 more possibilities in this 2004 style. Alright, so let's do our practice problem. In 1966, one type of Maryland license plate had 2 letters, so I'm going to make 2 slots for those 2 letters, followed by 4 digits. 1, 2, 3, 4. So these are digits, and and these are letters. So there are 26 letters possible, and digits there are 10. So total possible, we just crank out our calculator. 26 times 26 times 10 to the 4th. 606,760,000. Possible places. All right. We're going to start getting more specific. Permutation is an arrangement of items in a particular order. And so after you write this down, go ahead and highlight particular order, because the one that has to do with order matters in permutation. Permutation, particular order, P and P. Permutation, particular order. Combination, could care less, C and C. Permutation, particular order. All right, so I've been waiting for this moment all school year. We get to use the factorial. He's not only for punctuation, he gets everybody pumped up, he's jazzed, he's excited, but he does something cool. He takes, starting from your n value and counting down, all those values and multiplies them together until you get to 1. So if I were going 4 factorial, I would go 4 times 3 times 2 times 1. It's excited. It's multiplication. It's excited multiplication. Please write down that 0 factorial is equal to 1. We won't use it very often, but it'll ninja strike us when we're not expecting it. So 0 factorial is 1. You guys don't have to write this problem down, but we'll do the got it together. So let's look at how we're going to use permutation and the factorial in this problem. So finding the number of permutations of n items. In how many ways can you file 12 folders, one after another, in a drawer? We're going to use the fundamental counting principle. And so if you, my method is to use the slots. So you go, there's 12 file folders. And for the first one, think about this. If I have 12 folders to begin with, the first slot, how many options do I have to put in that first position? How many folders are there? 12. But unfortunately, for the next slot, I've already placed one in that first slot. So how many options are there for the second slot? 11. Now I have 2 folders placed in their positions. How many folders do I have left for the next slot? 10. And do you guys see the pattern? Now, instead of writing this all out, 12, especially what if I had 24 folders? What if I had 48 folders? That'd be a lot of, you could do it writing the slots and counting down. But we can just abbreviate this as 12 factorial. 12 factorial says all the numbers from 12 to 1 multiplied together. Alright, so if you pull up your calculator, the factorial button, this is just the one from my computer. The factorial button is right here, so I would go 12 factorial. Boop. And instead of, having to input each of these numbers and putting a multiplying sign in between each of them, I can just go 12 and then button push, and then we're done. So let's do this problem for number 2. How many ways can you arrange 8 shirts on a hanger in a closet? So I can write my dashes. And the first, so I've got shirts. So I start out with 8. So the first slot gets 8. But once I have that shirt already hung up, I only have 7 left on my bed to be hung up. 6, 5, and then we're going to go, etc. Can we just say that this is going to be 8 factorial once at the end of the day? And let's calculate that on our calculator. Easy peasy, lemon squeezy. 8 factorial. 8 shirts. There are 40,320 ways to arrange your 8 shirts. Goodness gracious. Here's my text right here. Mm-hmm. All right. So, in fact, let's just double test just in case while we're getting used to the new terminology. Eight times 7 times, oh shoot. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 40,320. Yay, so we know it works. Yay. All right, take note. So we got a note. There is a little formula for permutations. So remember, permutations, particular order, P and P. So when you care about order, the number of permutations of n items, I'll highlight it out, of a set arranged R. Okay, so we have n total items, but we're only arranging R of them. So say we have 10 paintings, and we only have 6 spots on our wall for them. Well, we're going to go n factorial, so that would be our 10 factorial. And in this case, in our example problem, we have 10 paintings, but only 4 spots for them. So that would be your 10 factorial divided by your 10 minus 4 factorial. And you can actually do that on your calculator. 10 factorial divided by 6 factorial. Easy peasy. All right, so let's apply this. So finding NPR, track. And by the way, people coming in for second, third, that's a big permutation. They use that example problem a bunch. So let's look at the problem, and then we will use and do the got it scenarios together. So if you're looking to write things down, you only have to write down the got it. So 10 students are in a race. First, second, and third students will win medals. Third places will win medals. In how many ways can 10 runners finish first, second, and third, no ties allowed? So we're going to use the fundamental counting principle. And that's, here's your first, second, and third place. Your first runner comes in, there's 10. Your second runner comes in, there's 9. Your third runner comes in, there's 8. So, by the way, this is how I got through. I like a picture. So most of the time, if I can use fundamental accounting principle, I draw a little picture and do it. But the second way, if you use permutations, and most graphing calculators have a permutation function on it, so it's pretty easy to do. So NPR, so we have 10 runners, but there's only 3 spots they can occupy. So that's n factorial over n minus r factorial, and we said n is 10 and r is 3. So that's 10 factorial over 10 minus 3 factorial. So that's 10 factorial, and if you look here, 10 factorial is 10 times 9 times 8 times 7, etc. 7 factorial is 7 times 6 times 5 times 4 times 6. This part has been it's been canceled with this part here. So it's interesting how that worked out. So the answer is 720 different ways that 10 runners can finish first. So you just go 10 times 9 times 8, or if you do it on your calculator, 10 factorial divided by 7 factorial. $720. Okay. Now let's change the scenario a little bit. In how many ways can 15 runners finish first, second, and third? So we just care about 3 of those 15. We'll do it the permutation way. When you get good, you'll do the subtraction automatically. So 15 factorial divided by 12 factorial. 2,730 ways. All right. Combinations are a little bit more complex in the fact that order doesn't matter. So if you're running a race and first, second, and third, the order matters. I want to be first, so I don't want to be that third place guy. So order matters in permutation. In a combination, order does not matter. It's like saying, I'm going to pick 5 students from a class of 30 to be in a group. In that case, it doesn't matter who is in the group first, just at the end of the day, there's going to be 5 total in that group. So combination is a little bit different. So go ahead and write the formula down. So the number of combinations of n items, chosen r items at a time. So it goes n choose r is n factorial divided by r factorial times n minus r. And please make sure you're choosing less items than you have available to you, or this would not work. So go ahead and write the example problem down too. If I have 5, so say I have, well, I'm going to adopt kittens. There are 5 kittens that are up for adoption, but I only want to choose 3. Doesn't matter which order that I choose the 3. You're going to go 5 factorial divided by 3 factorial times 5 minus 3 factorial, which simplifies down to 5 factorial divided by 3 factorial times 2 factorial. It's 120 divided by 6 times 2, and that is 10. So let's do a basic problem together. We have 15, choose 5. So we're going to go 15 factorial divided by 5 factorial times 15 minus 5 factorial. Simplify down is 15 factorial divided by 5 factorial times 10 factorial. So let's see how that goes in our calculators. So I'm going to put the 15 factorial on top. I'm going to go divided by, and I'm going to throw down some parentheses because I got 2 items down here. I'm going to go 5 factorial times 10 factorial, close my parentheses, hit my equal sign, and I get 3,003. All right, let's look at a couple scenarios together so we can correctly identify if we need to use combination or permutation. So if we look here, a chemistry teacher divides his class into 8 groups. Each group submits 1 drawing of the molecular structure of water. He will select 4 of the drawings to display. In how many different ways can he select the drawings? There is no reason why order is important. So you guys are kind of detectives. You have to figure out if order matters or order doesn't matter. It doesn't say that he's going to put them in a certain particular order on display. He just says he's going to pick 4 out of the 8 groups. So we use combination. N is 8, R is 4, and when we do the math on it, we get 70. There are 70 ways to select a drawing. Okay, let's look at B. You'll draw winners from a total of 25 tickets in a raffle. The first ticket wins 100, second ticket wins 50, third ticket wins 10. In how many different ways can you draw the 3 winning tickets? The values of the tickets depend on the order in which you draw them. Order is important. You have to use permutation. So when we have 25 and we're choosing 3 to be our winners, but order matters, you got 25 and 25 minus 3. That simplifies to 25 divided by 22 factorials. And that's 13,800. All right, so let's do a sample problem. In problem 5A, how many possible ways for the teacher to select and arrange the 4 drawings from left to right on the wall? So in this scenario, does order matter? From left to right on the wall. So in this case, because he's arranging the 4 drawings, order matters, and we're going to use permutation. So we have 8 to choose from. We're going 4. So that's 8 factorial divided by 8 minus 4 factorial. Divided by 8 minus 4 is 4. It's 1,680. So it's 1,680 ways to arrange the pictures.